Okay, so we're going to do question 3 in the Midterm exam. So in this question, we are given a utility function for a consumer, which is equal to x to the power half plus y. Okay, so this is a quasi-linear utility function that that Pavlos already went through in the past exam paper. Okay, so part A is asking you to derive the Marshallian demands for x and y. All right, so it's pretty straightforward. So in order to find the Marshallian, which is basically the normal demands for x and y, then we would just have to set up the problem where we try to find x and y in order to maximize the utility for consumer subject to a budget constraint. Okay, so what we want to do is to maximize the utility function for the consumer, x and y equal to x half plus y. Okay, by finding the optimal value of x and y subject to a budget constraint where px times x plus py times y equal to income m. Okay, so we know that the optimal condition in this case is just going to be where the consumer is maximizing utility at the point where marginal rate of substitution is going to be equal to the negative of the price ratio. Okay, so marginal rate of substitution is the negative of the marginal utility ratio. So I got marginal utility of x on marginal utility of y, and that just has to be equal to the negative of the price ratio px on py. All right. So now marginal utility of x is, so if I differentiate the utility function over here with respect to x, I get half of x to the power negative half and plus y, which just disappear. Okay, and marginal utility of y is just going to be equal to 1. Okay, and so equal to px on py. Now I get rid of a negative sign on both sides of this equation. Okay, so from here I should be able to find the values of x. So this is just basically half of 1 on x to the power half, so that it's just 1 on 2 square root of x. Okay, so it's x to the power half is square root of x, and because we have a negative sign, so we move that to the denominator, the negative sign will disappear. Okay, and that is equal to px on py. So I'm solving this equation, I'll get 2 square root of x is equal to py on px. Okay, and so therefore, square root of x is equal to py on 2px. And so therefore, x, if I square both sides of this equation, I get py squared equal to 4px squared. Okay, so this is the Marshallian demand for wood x. And from the budget constraint, I should be able to find the optimal amount for wood y. Okay, so from the budget constraint, I know that px times x star, which is py squared divided by 4px squared, plus py times y star is equal to m. And so therefore, if I got px, we cancel with one of the px. Over here, I got py squared divided by 4px plus py on y star equal to m. So py times y star is equal to m minus py squared divided by 4px. And so y star is just going to be equal to m divided by py minus py squared on 4px divided by py. So that will cancel one of the py over here divided by 4px. Okay, so this is the optimal amount of y star. Okay, so part B is asking you to find the Hicksian demand for wood X. So now we know that the Hicksian demand is just going to be found by minimizing the expenditure, okay, subject to the fact that we want to achieve a certain level of utility. Okay, so our problem in this case is just going to be the minimum. We try to minimize the expenditure, which is px times x plus py times y, okay, by finding the Hicksian demand for good x and y, subject to the constraint that we want to achieve a certain level of utility, okay. So subject to the constraint that the utility, which is x half plus y, it has to be equal to 0. Okay, so again, the optimal condition for this it's going to be the same where marginal rate of substitution it has to be equal to the price ratio. So it's negative marginal utility of x on marginal utility of y has to be equal to px on py. Okay, so either for Hicksian or for Marshallian, the optimal conditions remain the same, just like what we did in the review session. Okay, so this is just going to give us the same optimal conditions as above, which is this. Okay, so from this optimal condition, we found that x squared x star, or I call hash, okay, which is Hicksian demand, which is going to be equal to py squared divided by 4px squared. All right, so it's just from here, because the optimal conditions remain exactly the same. So what we found is the same. All right, so the Hicksian demand for x is the same. The only thing different is now we substitute this into the optimal constraint over here. Okay, so I'll just say this is the star constraint. So I'll get x to the power half, which is py squared on 4px squared, everything to a power half, okay, plus y, I say y hash, and that is equal to u0. So square root of this is going to give me py onto px, okay, plus y hash equal to u0. And so therefore y hash is going to be equal to u0 minus py divided by 2px. Okay, so this is the Hicksian demand for wood x and y. And now, so part C, is asking you if we have an increase in income, how is that going to affect the Marshallian and Hicksian demand for wood x? So as you can see from here, this is the Marshallian demand for x, and this is the Hicksian demand for x. And it doesn't depend on income. As you can see, there's no m in this function. Okay, there's no m in the expression for the Marshallian and the Hicksian demand for wood x. So therefore, if you have an increase in income, it has no effect to the demand for wood x. Okay, right? So I'll say now, because x star, which is the Marshallian demand, equal to x hash, and equal to 4, so at py squared on 4px squared, which has no m in them. Okay, so therefore we know that x star and x hash do not depend on income. Okay, so therefore an increase in m will not have any effect. Okay, so do not affect the Marshallian and the Hicksian demand for wood x. Okay,